Welcome to our 4.2 notes, linear models. This is a lesson I think everything you see is pretty much going to be a review. So we're going to start with linear models in the form f of x equals m times x. Take a look here is what the graph of a function of the form f of x equals m times x would look like. Obviously this graph, the graph of this function would be a straight line. It has a slope, it has a positive slope, and hence, since it has a positive slope, it would be an increasing function. Okay, the graph will pass through the origin, and you might remember this from Algebra 2, y is directly proportional to x. Okay, that means that as x increases, y is going to increase, and that increases at a constant rate. This linear model is often used for what we call conversion graphs. So a conversion graph would be a simple conversion, like if we are converting one unit to another. So we have one unit versus another number, or perhaps a currency conversion where we convert one currency to another, and that change is going to be constant, so it would be a linear function like this. Okay, to find the gradient in the IB world, we call gradient is what you're used to using the word slope. So to find the gradient, that's something familiar to you. We'll just use the slope formula. Remember, slope is a ratio of a vertical change to a horizontal change. So to find that vertical change, we'll take the difference in y's, and to find that horizontal change, you'll take your difference in x's. Okay, so let's take a look at an example. In example 1, it says 1 mile is equivalent to 1.6 kilometers. So let's draw a conversion graph of miles to kilometers. So we're going to convert miles to kilometers. So that means miles is going to be our independent variable. So let's let x represent number of miles, and let's let y represent then number of kilometers. Now remember, in IB, whenever you draw a graph, you want to always tell us what x and y represents, and then also you want to indicate your units. I'm going to count, since miles and kilometers, we're usually talking about larger numbers, I'm going to count by tens for miles. And then for kilometers, let's count those by 20s. Oops. 40, 60, 80, 100, 120. Okay, so I'm going to pick a pretty point. I'm going to, let's see, if I take 50 and multiply it by 1.6, I get 80. So I call that a pretty point because 50, 80 are just easy points, easy coordinates to graph. So let's plot that point 50, 80, okay, and then use the origin, and then use a straight edge to draw a straight line. And we have completed part A, which says draw a conversion graph that shows the conversion from miles to kilometers. Okay, now part B says find the gradient of the line. Remember, when you see that word gradient, that means slope. So for B, we're just going to find the slope. So we'll take the difference in y's. Let's just use these 2 points. Let's use the point 50, 80. And the origin, which of course has coordinates 0, 0. So my difference in y's would be 80 minus 0, and my difference in x's would be 50 minus 0, which is 8/5, and then that's equal to 1.6. All right, and then point C says, hence, write down the model for k of x, where k of x, your output, is the distance in kilometers, and x, your input, is distance in miles. So that function, or that model, would be k of x is equal to 1.6, that's our slope, times x. Okay, the next thing we're going to take a look at then are linear models of the form. In IB, we say f of x equals mx plus c. You're used to seeing that as a b, but it means the same thing. That constant is a sorry about the bell, that constant is your y-intercept, and of course m is your slope. So when we have an equation like this, or a linear model like this, x and y are not in direct proportion, and the graph does not go through the origin. In example 2, it says, in a chemistry experiment, a liquid is heated and the temperature at different times is recorded. The table of contents for one student is known. So here we have a table that shows us for our independent variable time and then temperature in degrees Celsius. So in letter A, we are going to draw a graph for this function. So let's go ahead and label our x's. We're going to let x represent a number of minutes. So x is number of minutes. And then y is going to represent degrees Celsius. You always want to, when you label your axes, make sure you quantify them. Make sure you describe them in terms of a number or quantity. Okay, so let's put some units on our x-axis. How about we let's count by twos. So 0, 2, 4, 6, 8, 10, 12. And then for our temperature, let's count by tens. So 10, 20, 30, 40, 50, and 60. Okay, and then let's plot our points. We have our first point would be at 2:30. Okay, the second point at 4:40. The next point at 6:50. And then our last point is going to be 9:65. So we're going to go off the graph a little bit. So 9 is going to be halfway between 8 and 10. And then we need to go up to 65. We're going to have to kind of guesstimate where that is because I should have given us a slightly larger graph. So it's going to be right about here. Okay. And then grab a straight edge, and you'll want to draw a straight line through those points. Okay. Then letter B says, let's see, find a model T of X, the temperature with respect to time for these data. Okay, so it should look like let's go ahead and write down our function should look like this. T of X equals mx plus c, where m is your slope and c is your y-intercept. So let's just take a minute to find the slope. So I'm just going to grab a couple of points. I'm going to grab this point, the point 2:30, and then the y-intercept 0:20, and use those 2 points to find the slope. So my difference in y's would be 30 minus 20, and my difference in x's would be, let's see, 2 minus 0. So that turns out to be 10 halves, or 5. And then as you look at the graph, you can see that our y-intercept is 20. So our function is going to be t of x is equal to 5x plus 20. Okay? And then letter C says, use the model to predict the temperature of the liquid after 8 minutes. Well, remember, temperature is your output, and minutes would be your input. So let's put 8 into this function. In other words, we're going to evaluate t of 8. So t of 8 would be equal to 5 times 8 plus 20, which is 40 plus 20, or 60 degrees. And then that was letter I, and then letter double I says the time, we're going to predict the time taken for the temperature to reach 57 degrees. So here we know the output is 57. We need to figure out what the input is. So let's set it up like this. Let's say 57 is equal to 5x plus 20, and then we can quickly solve that equation for x. And let's see, x turns out to be 37/5, or if we want to convert that to a decimal, that would be 7.4. Now remember, we were trying to find the input, and input is minutes, so 7.4 minutes. Okay, and then the last thing we're going to do is take a look at linear models involving simultaneous equations, or you probably have heard those called a system of linear equations. So let's take a look at this example. We have a carpenter who makes wooden tables and chairs. It takes him 10 hours to make a table and 4 hours to make a chair. The wood costs $120 for a table and $40 for a chair. So the first thing we're going to do is find a model for A, the time required to make the tables and chairs. Well, the first thing we need to do, the reason we need a simultaneous set of equations is because we're going to have two unknowns. So what are those unknowns going to be? Well, in this case, it's going to be number of tables and number of chairs. So let's go ahead and set that up initially. Let's let x represent number of tables, and then we'll let y represent number of chairs. Okay, so to write a function that represents the time required to make tables and chairs, well, it takes him 10 hours per table, and we have X tables, 4 hours per chair, and we have Y chairs. So our function would look like this. T for time, let's just use T for time, would be 10 hours per chair or per table times X tables plus 4 hours per chair times Y chairs. Okay, and then letter B says find the cost of making the tables and chairs. Well, we know that each table costs $120 and each chair costs $40. So let's write a cost function. So each table is $120 multiplied by X, the number of tables, that's the total cost in tables, plus each chair costs $40, and then times the number of chairs, which would be Y. Okay, so there's our system of simultaneous equations. Now let's take a look at this next part that says the carpenter works 70 hours in 1 week and spends $760 on wood. So how many tables and how many chairs did he make? So we'll set up the system like this. Let's see, 10x plus 4y represents the total time, and he spent 70 hours total. And then remember, cost is 120x plus 40y, and that total cost was 760. So at this point, you can solve this system or the set of simultaneous equations by graphing or substitution or elimination, or since this is math studies and we are depend on calculators quite a bit, here are the steps that you would follow. You may have done this before to solve a system of linear equations. So when you do, the calculator will give you this result. They always put the calculator puts the results in brackets, and you're going to get brackets that say 3, 10. So what that represents is this is an ordered pair where this is your X value and this is your Y value. So that means that the carpenter made 3 tables and he made 10 chairs during that week. All right, so you can go ahead and get started on your homework, and if you have any questions, be sure and let me know.